Hello guys, let me introduce myself. My name is Kurniawan Soleman with NM2 21011060118. Okay, let's get into the journal discussion. Let's get to the title.
I raised the journal title about the max flow min-cut theorem. Abstract: the max flow. Min-cut theorem is a fundamental result in network flow theory and combinatorial optimization. It states that in any flow network, the maximum amount of flow that can be sent from a source to a sink is equal to the total capacity of the smallest cut that separates the source and the sink. This article discusses the basic concepts, formal definitions, proof of the theorem, related algorithms, and its applications in various fields. 1. Introduction. Flow networks are crucial components of various systems where the transportation of goods, data, or resources needs to be optimized. The max flow min-cut theorem stands as a cornerstone in the study of such networks, bridging the gap between maximum flow in a network and the minimal cuts required to separate the network into distinct components. This paper aims to explore the max flow min-cut theorem in depth, covering its fundamental concepts, historical background, applications in diverse fields, and practical implications. 2. Literature review. 2.1 Historical background. The max flow min-cut theorem was first introduced by Ford and Fulkerson in their seminal 1956 paper, Maximal Flow Through a Network. Their work laid the groundwork for the modern study of network flows, providing a robust theoretical framework for understanding and optimizing the flow of resources through networks. 2.2 Fundamental concepts. The theorem can be stated as follows. In any flow network, the maximum amount of flow from the source to the sink is equal to the total capacity of the minimum cut that separates the source from the sink. Key concepts include flow network, a directed graph where each edge has a capacity and each edge receives a flow that does not exceed this capacity. Maximum flow, the greatest possible flow from the source node to the sink node under the given constraints. Minimum cut, the partition of the vertices into two disjoint sets such that the source is in one set, the sink is in the other, and the capacity of the edges crossing the cut is minimized. 2.3. Proof of the theorem. The proof involves constructing a residual graph and repeatedly finding augmenting paths until no more can be found. When no augmenting paths remain, the value of the flow equals the capacity of the cut in the residual graph. This duality between flow and cut underpins many of the applications and algorithms derived from the theorem. 3. Basic concepts. 3.1 Flow network. A flow network is a directed graph, I-G-R-V-E-A, with vertices. V is the set of vertices. Edges. E is the set of edges. Capacities. Each edge, U-E-V, E, has a capacity, C-U-V, indicating the maximum amount of flow that can pass through that edge. 3.2 Flow. A flow in the network satisfies capacity constraint for each UAV, E, the flow, F, UAV, X, C, UAV, flow conservation, for each vertex V, V, A, S, and T, else. The sum of flow into V equals the sum of flow out of V, UVF, UAV, R, WVF, VW, and 3.3, cut-a-cut, S, T. In a network is a partition of the vertex set V into two disjoint subsets, S and T, such that SS and TT. The capacity of the cut is the sum of the capacities of edges that cross from S to T capacity, SET, US, VTC, UAV, 3.4 Minimum cut. A minimum cut is a cut with the smallest capacity among all possible cuts that separate the source and the sink. 3.5 Maximum flow. The maximum flow is the largest possible value of flow from the source, or SAM, to the sink, ATG, that satisfies the capacity and flow conservation constraints. 4. The max flow min-cut theorem. The theorem states maximum value of flow, minimum capacity of a cut. 5. Proof of the theorem. The proof of the theorem involves several key steps. 5.1 Definition of maximum flow. Define a flow F from the source, S to the sink, T. 5.2 Residual graph. The residual graph GF is constructed based on the original capacities C and the current flow F. The residual graph shows the remaining capacities of the edges. If F, UAV, is the flow on edge, UAV, then the residual capacity CEF, UV, ARF, C, UAV, F, UAV, 5.3. Augmenting path. An augmenting path is a path in the residual graph that allows an increase in flow from S to T. Flow is increased along this path until no more augmenting paths can be found. 5.4 Cut and flow relationship. Once no more augmenting paths exist, the residual graph indicates that the flow value equals the capacity of a cut in the residual graph. This means that no further increase in flow is possible without violating capacity or flow conservation constraints. 5.5 Duality. By using duality arguments, it can be shown that the maximum flow in the network equals the minimum cut capacity. This involves demonstrating that every increase in flow corresponds directly to a reduction in the cut capacity. 6. Related algorithms. 6.1 Ford-Fulkerson algorithm. The Ford-Fulkerson algorithm is an iterative method for finding the maximum flow in a network by using augmenting paths until no more can be found. 6.2 Edmonds-Karp implementation. Edmonds-Karp is an implementation of the Ford-Fulkerson algorithm that uses BFS, breadth-first search, to find augmenting paths, ensuring a time complexity of O, VE2, 7. Practical applications. 7.1 Network design. The theorem helps in designing optimal networks, ensuring maximum capacity for data or material flow through the network. 7.2 Network reliability. By finding the minimum cut, we can determine critical points in the network whose failure would cause total network disconnection. 7.3 Supply chain optimization. In supply chains, the theorem is used to determine the maximum possible throughput and identify bottlenecks in the distribution system. 7.4 Bipartite matching. In bipartite matching problems, such as job assignments or scheduling, the theorem helps find the maximum matching that optimally pairs elements from two sets. 8. Discussions. 8.1 Algorithmic implementations. The Ford-Fulkerson method and its implementation via the Edmonds-Karp algorithm are widely used for finding the maximum flow in networks. The Edmonds-Karp algorithm, which uses breadth-first search, BFS, to find augmenting paths, ensures a polynomial time complexity of O, VE2. This efficiency makes it practical for large-scale networks. 8.2 Real-world implications. In real-world applications, the max flow min-cut theorem has been pivotal. For instance, in telecommunications, ensuring that data packets flow efficiently across networks directly impacts service quality. In logistics, optimizing the flow of goods from warehouses to customers can significantly affect delivery times and costs. Moreover, in healthcare, optimizing the allocation of resources such as vaccines or medical supplies can save lives during emergencies. 8.3 Limitations and challenges. While the theorem provides a strong theoretical foundation, practical challenges remain. Real-world networks often have dynamic changes, such as fluctuating capacities and varying demands. Additionally, computational limitations can arise in extremely large networks, where even polynomial time algorithms may become infeasible. 9. Conclusion. The max flow min-cut theorem remains a cornerstone of network flow theory, providing critical insights and tools for optimizing various systems. Its applications range from network design and supply chain management to matching problems and network reliability. Despite the challenges, its relevance and utility in solving real-world problems make it an indispensable part of operations research and optimization. Thank you for watching. Don't forget to subrec and like.